Okay. Yeah, so the way I like to do these reviews is pretty much to just throw some practice problems at you. These would have been problems that, oh, that would have been a good problem I could have had on the test. And then I just didn't put it on the test. I haven't written the test yet, by the way. But anyway, I'm not going to put these exact problems on the test, but you can obviously expect that I'll have a lot of these ideas there. And yeah, so let's just start. I'm going to start, I'm going to go a little bit out of order, and I am going to, well, I want to type up these questions after the review to send them. Somebody had asked if I could like write out what the questions were for the review session. So maybe one of you is taking notes and I'll be able to steal from you guys which order I do, because I kind of jump around just depending on what I feel like doing. Okay, so let's start with something that's not going to be too taxing on us here to get rolling. And this is going to be number one, is going to be a true false set of questions. Now, I'm probably not going to do true false on the exam. I used to do that with very mixed results, and I never liked them myself as a student because people tend to they second guess things like, oh, there's been two false in a row, so the next one has to be true, and it becomes a mind games thing. More likely what I would do is I would tell you, here is a true statement, prove it, or here is a false statement, give me a counterexample. Okay, but for our purposes in the review, I'm going to state it as a true false for us to think about. So here it is. If A and B are dense subsets of R, then, and I'm actually going to have two parts to this. So part A is going to be, so is a union B. And then part B is going to be, so is a intersect with B. So if I start with two dense subsets of R, the question is, would their union still be dense, and would their intersection still be dense? And actually, prior to asking this question, I might have like a part A. If this was on the actual test, I might have part A of the problem would be define a dense subset of R. And then part B would be to use it to like answer this question. So let me just recall for you here what a dense subset is, and then we can be thinking about whether these statements are going to be true or false. So a dense subset, I'll just say S is dense in R if for all X less than Y in R, there exists a little s in capital S with X less than S less than Y. So I can always squeeze an element from my set in between any two real numbers, okay? And the quantifiers are very important here. So if you don't say there exists an S, then there could be confusion about what I mean here, right? Or if I don't say for all X less than Y, then this statement becomes a little more ambiguous. So if I do ask you to write definitions down, you know, it really does need, for full credit anyway, it's going to need to be very carefully written down with all the important quantifiers in there. It's just, that's one of the things about 350 that can be challenging is just getting the exact statement down. So just really work on that. If you've been making flashcards, it's good to quiz yourself with those flashcards right up until test day, I think. Okay. All right. So with that definition in mind, and by the way, if you guys are out there in Zoom, you're welcome to jump in as well. Either in, I'm going to try and turn on my chat box here. So you guys are also welcome to jump in, but I'd love to get feedback from anyone about whether they think part A is true or not. Okay, yes, 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 yes. Everybody kind of thinking yes. Everybody in the room is saying yes, or thinking yes. And does anybody have like a reason? Because of course I would want to give that you are right. It is true. So part A is true. I'm wondering if anybody would have like a good reason they could explain it with.
if we want anything between X and Y, and then you're choosing from things in A or B, and you already know that A is dense, you could just always pick something from A.
Exactly, because A is already dense in R, then I can find an element of A between X and Y, and that element, of course, lives in A union B as well. You're only making your set larger, right, when you take a union. So if you had something that was already dense to begin with, and you just throw more points into that set, it's just going to make it more dense, right? So this would definitely be true. And so then we would want to give a justification for that. I kind of gave a verbal sort of explanation in words. But what we could say here, if we wanted to make it really formal, is we could say let x less than y in R. Right? So fix your two numbers x and y in R. And then you could just say, since A is dense in R, there exists a little a in capital A. But A is a subset of A union B. So I'll go ahead and that's the key point, right? There exists an A in A union B with X less than A less than Y. Okay? And so that pretty much just straight from the definition gives a proof. Okay? So it doesn't have to be anything too long. And there may be other ways of phrasing things like this. But this would certainly do nicely. Okay, I really will want to know that you understand the concept. It's the most important thing. So things like the quantifiers, as I was talking about, is really important because the meaning of what you're saying is so dependent on, is it for all, is it for some, stuff like that. So just really try to take some care with those sorts of things. Okay, any questions on that? That's just kind of a warm up tonight. What about part B? Instead of taking a union of two dense sets, what if I intersect two dense sets? Anybody have any thoughts about that, either in Zoom or in person? Okay, now I've got everybody shaking their head no in the room, right? And I am right with you on that. I would say this is false as well. And when something is false, what we're going to want to probably try and do is give a counterexample. So we would need to think about, could we set up sets A and B, make them, specific sets, and each of these needs to be dense. So you can think about, well, what dense subsets have we learned about? Like, what do we know would be a dense subset? And then hopefully we can do it in such a way that the intersection is like nothing. Does anybody have an idea for what dense subset we could maybe start with? Q.
Rational is rational.
Yeah, how about Q, right? The rational numbers, those are definitely dense. Sorry, I get my chat box open here. Yeah, Ayushi, beautiful. Has the same thing in the chat. Basically, we can take the rational numbers as one of our sets. I'll call that A. And then the irrational numbers, we could call that B. Both of these were proven to be dense in R. The first one is actually a theorem from class. And guys, I don't expect you to know the theorem numbers because it's just our book, right? As soon as you find a different book, the numbers won't matter, right? So you can just say theorem from class. And then the second one about the irrationals, that was actually from the homework that you just turned in last week. So this would be from homework. And you could just say that from homework. If you're not even sure, like I don't even care if you're not even, you could just say, we learned this in class or something very general. I'm not expecting people to memorize, oh, well, what was in the group work versus what was in the homework versus what was in the lecture. Doesn't matter to me, as long as it was actually something that we did, right? Because I haven't missed class so far, so I know exactly what we've done and what we haven't done. Okay, but yeah, so both of those, and the statement is A and B are both dense. So A and B are both dense, according to the homework and the class theorem. Dense in R. However, what is the intersection? That's very empty. It's as empty as it gets. It's the empty set. And so the empty set is not dense. We can just add that, which is clearly not dense. I have to be a little careful using the word clearly because what's clear to one person might not be clear to another. If something really is clear to you and you're wondering, oh, do I really need to justify it? Come ask me during the exam. You know, you could just say, here's what I'd like to say this. Do I need to justify it if you're really not sure? But something like this, I mean, obviously you can't find an S from the empty set that's between two numbers X and Y, so you're not gonna have any doubt about that, right? Okay, so I think, you know, that's a nice little warm-up problem. You know, so you might think about this concept and think, well, what other questions could we make that would be interesting that has to do with this concept of denseness? So I think I will, I have one here, but maybe I'll come back to it. I think I might come back to it. You could think about, well, how else, instead of taking unions or intersections, what else could we do? What other ways could we take some known set that's dense and create something else out of it, right? This is kind of my suggestion from even the beginning of the semester about how to sort of like, you know, create these little quizzes for yourself. Right? So I'll give you one example. Instead of union or intersection, we could ask, well, what about set difference, right? Or we could, I'm not gonna tell you yet. I'll come back to it. There's other things we can do, maybe involving functions instead of just sets like this. But let me go on for now because I'm getting too excited. This is always my problem. I just want to jump all over it right away. Okay. Yeah, so let's go on to something else. Here's another type of question that would be very likely for the exam. Let's decide if the sets below are finite, countable, and or uncountable. And this is kind of something you've seen already. I gave a quiz problem that was like this. I had a couple of sets for you to play with, and I would just ask you whether they're finite, countable, and or uncountable. So this is, you circle all of the right answers. So remember, if you circle finite, you should automatically circle countable also, because anything that's finite is also countable. Yeah, so that's something to keep in mind. So you have to sort of circle all correct answers here. So here's the first one. Let's take S to be the set of expressions of the form m divided by 2 to the power of k, where m is an integer and k is a natural number. Oh, I'm gonna need more room here. Sorry, guys. So I'm not done with that yet. I'm going to take that thing and do a union of that with another set. And the second set here is going to be expressions of the form L over 3 to the little n, where again, L is an integer and n is a natural number. Okay, so I'm going to make this set like so. And let's just start with part A. I won't write all the parts down yet. Let's just get part A, kind of a moment to think about this. So what kind of numbers do I have in here, by the way, that we're looking at? There's natural numbers, there's integers, and do we know about whether those are finite or countable or uncountable? They're countable, right? Yeah, exactly. The integers are countable. By the way, that's another fact from class. You can just state that. You don't have to like stop and prove that. The natural numbers are, of course, countable. They are sort of the defining set that creates the definition of what countable means. So Z is countable and N is countable. So the number of expressions that you can build here is also going to be countable. You essentially have to think of it as almost like it's a cross product of Z with N. You're taking pairs of values consisting of an integer and a natural number. And you could actually create a function like that if you wanted to. Okay. But we don't really actually have to work that hard because although it is true, we have natural numbers and we have integers here. What kind of expressions actually are these? They are in Q, right? They are rational numbers, right? And so are these. This is basically the same thing. So you're looking at fractions whose denominators are either a power of 2 or a power of 3. In other words, it is sum of Q. It's not the whole Q, but it is sum of Q, right? So actually, I could say for sure that this is countable, right? And the reason or the proof of that could not be really any easier. The point here is that S is a subset of Q, right? You can just simply note that, and Q is already countable. Right, guys, we do know that Q is countable. There were a couple people on the quiz that were telling me it was uncountable. Q is definitely countable, and a subset of a countable set is countable. So by a proposition in class, this means S is countable. Okay, so it's countable, that if it's countable, then it's automatically not uncountable. So we don't have to worry about that. But it's also not finite because of course the integers are not, nor are the natural numbers, okay? So I'll just say, since Z and N are not finite, neither is S. If you didn't justify that one, I probably would let it go. It's kind of clear, I would say. It's the main thing I'm really looking for here is that you have a subset of Q. Yeah, it's just a subset of Q. Did anybody think of any other ideas for how to kind of explain this one?
Can we use theorem 2.4?
Oh, sorry?
Theorem 2.4.
Yes, one of the most important theorems on the subject of cardinality is theorem 2.4, which says that a countable union of countable sets is countable. Just be sure, but if you're going to cite that, guys, be sure that by the time you've written it down, you've written the word countable 3 times. There were some people in the quiz saying a union of countable sets is countable. And I was like, no, it has to be a countable union of countable sets. So you just really have to state it correctly. Yeah, so just as an alternative solution, you don't really need to use this here, but an alternative would be to say S is a countable union. The countable union is referring to the fact that how many sets are you taking the union of? And the answer is there's only 2, right? So there's 2. It's a union of 2 sets. 2 is finite, obviously, and finite implies countable. So this is a countable union of countable sets, right? Hence, countable. And again, I will write down the theorem number here, and Crystal knew it already, but if you didn't remember the number and you just said by a theorem from class, that's good enough for me for an exam, okay? So yeah, so that's definitely a theorem worth committing to memory, and it's probably even worth reviewing the proof of it, to be honest. It's not that long or involved of a proof, and it actually does, I think, have some good insights in it. So that's worth a little bit of your time. Okay, that theorem there. In this problem, we didn't really need to do this theorem 2.4 because we really just have a subset of Q to begin with. But there may be situations where you really do need to use that theorem. Okay, people feel all right with that? Any questions so far? Okay, great. Let's do a part B then. And I'm in no hurry here, guys, because again, I've got some problems. If I don't get through everything, I'll just do them again on Wednesday. And so please definitely let me know if there's questions as we go along here. Definitely want to try to help out. Okay, so let's do another one. Let's do S equals the real numbers crossed with just a singleton set with some little a. A is just like some fixed real number here. Let's just imagine we have that. Okay, so we take the real numbers and we basically are making pairs. This is a Cartesian product, right? So the elements here are pairs. The first slot has to have a real number in it. The second slot actually has to have the A in it. That's really what it is. So, yeah, any thoughts about this one? Do we think this might be countable, uncountable, or defining?
Thanks.
Uncountable? Okay, uncountable? Uncountable. Everybody in Zoom okay with that? Uncountable? Right. Yeah, this one is going to be uncountable. And that's really, well, so yeah, so this is uncountable. And can somebody tell me what's the main fact behind why it's going to be uncountable? Because R is uncountable. If you don't really know like the full justification of it, like just write down everything that you know that is related. Guys, I love to give partial credit. So this would probably not get you totally full credit. It would probably get you a lot of credit though, knowing that R is uncountable. And again, this is a theorem from class. I don't even remember which one it is, but it's in that same section. You can find it. And the reason I say this might not quite give you full credit is because you haven't connected the R with the S here. So R is uncountable, but the question is asking you about S. Is S countable or uncountable? So what is the bridge, or how can we make a bridge between R and S?
Isn't S just a subset of R?
I would say S and R are actually not really comparable that way. S is a universe of pairs of entries, whereas R is just individual real numbers. So they're not really, you can't really say that they are, like one of them is inside of the other or anything like that. But what could we do to make a bridge here?
Would it be wrong to say that the Cartesian product of two uncountable sets would give you something?
That is actually true. Yeah, if you take the Cartesian product of two uncountable sets, it will be uncountable. But I have two comments for you. First of all, this one's not uncountable because it only has one thing in it. So this is not really a Cartesian product of two uncountable sets, but it is actually true. I can weaken what you just said and still have it be true, which is that if I take one uncountable set and cross it with anything, the whole result will be uncountable. So if you wrote that down, if you said S is uncountable because we have a Cartesian product of an uncountable set with something else, I would give you something for that, but I would probably say to you that, well, but that's not really explaining why. Like I would then want you to prove your statement. Like, why is it true that if you take an uncountable set and you cross it with something else, that it's still uncountable? So I think it would definitely be worth writing that down though. Is that a hand?
Sure,
Yeah.
because R cross A, it does not twiddle then.
Okay, R cross A does not twiddle N. That would again, same thing as what she said. I would say, okay, you're right. The definition of uncountable is it doesn't twiddle N, but then I would be coming back at you and saying, oh, but how do you know that R cross A does not twiddle N? Right, so I would want to have that justified as well. Yes.
I guess would it be safe to say that like the cardinality of S is greater than or equal to whatever R or A is?
When we get into these issues with infinite sets, the comment here was, could we just say that the cardinality of S is greater than or equal to the cardinality of R or something like that? Because these sets are infinite, that's kind of not very precise. It's good intuition, but I'm looking for something that is absolutely irrefutable, a robust way to convince me that if R is uncountable, then so is S. I'm looking for a bridge. And when I say the word bridge, what do I really mean?
Function.
A function. I mean a function, right? I can make a function between these two sets, R and S. And if that function is a bijection, right, then the two sets twiddle each other, right?
Mhm.
And if one of them's uncountable, then so's the other, because that was one of our propositions, right? So that's exactly what I would do. What I would do is I would define I would define, so all these other ideas that you had, guys, were great. You would get definitely partial credit for writing those observations down, but to really make it precise, I would want to make a bijection. So I might define f going from R to S. When you're writing down a function, guys, be sure you tell me what is your domain and what is your codomain and what the actual function is. So I'm gonna plug in a real number, I'll call it x here, and then I have to tell you what is the output going to be. So the output has to be something in S, which means it needs to be a pair of outputs here. And what would be the output, do you think? How would we define this function? Is it just x and a? It's just x and a, exactly. It would just be x and a. So you just put that in there and that would be your function. Now, some of you might also be thinking, well, could I define the function from S to R instead? That would totally be fine. You would have a basically just turning this around. These would be the inputs and these would be the outputs. Either way, it is totally okay. This one, in my view, is pretty clearly a bijection. So we could say that. Clearly, F is a bijection. Does anybody want me to write it out? Maybe I should. So if you just wrote that this was clear, I would take that. 100% fine. But let's just say I wanted to show that F is 1-to-1 and on to, just because it never hurts to practice this a little bit more. This is also part of what chapter 1 is about for our exam. So for F to be 1-to-1, we would assume that F of what? X equals F of Y. Right, and then our goal is to show that x equals y. Okay, well, let's just write what this means. F of x equals f of y. That tells me that the point x comma a is equal to the point y comma a. And when you have 2 points that are equal, then their slots have to be equal, right? So then obviously the a matches with the a, but then the first slot also has to match up, so x has to equal y, and that's all there is to it. So you see, this is not a very hard verification, but just so we kind of get the formatting, we can write it out one time here. We also would need to show that F is onto, be the other part. And for the onto, we just have to pick something in the codomain in S, right? So S consists of, so when you're introducing some arbitrary element of S, you want to make sure it has the right form for something in S, but it shouldn't look like it was concocted out of the outputs of F, which is so tempting to do, right? So you when you're writing down what an element of S looks like, try not to look at what F is. Just look at this thing here and say, what would something in S look like? I just look at this to figure that out, right? So let's see, it's got to be a pair, let's say X comma A, right? Be an element of S. So you grab that arbitrary element. This was not envisioned out of knowledge of what F is at all. It's just, here's what something in S looks like, okay? And then we have to find a preimage. When we're verifying the onto part, we have to find a preimage. Now, sometimes to do that, we have to do some sort of scratch work on the side to sort of figure out what is the preimage of this point. In this case, I don't think we need to do that, right? Because you can just kind of see it directly. And if you can see it directly and you just want to write it down, go ahead and do it, right? Obviously, it's going to be f of x that hits that point x comma a. So then we just put our check on that, and yep, we have a bijection. Okay? So R is uncountable. We already stated that. Now we have a bijection from R to S. And so finally, by a proposition from class, S is uncountable. So this one is uncountable. Okay. Great. Any questions on that one so far? Perfect. Let me give you one more on this, okay? So we'll practice one more. This is going to be part C. And part C, again, I'm gonna ask, is it finite, countable, or uncountable? And I'm gonna use, I'm gonna do something we haven't really talked about. This is script P of n, which is the power set of n. So this is the power set of the natural numbers. And just in case anybody's not familiar with this, because this is not something I've talked about, the power set is just the set of all subsets of, so the set of all subsets of the natural numbers. Okay. So the tempting thing here to do is to say, oh, well, the natural numbers are countable. And so I'm dealing with something about that. So then this has to be countable. That's kind of the surface level first thought you might have, okay? But we do want to think carefully, you know, so if we need to, we can maybe just get an idea what the objects of this power set are. Every subset of the natural numbers. So there's obviously the empty set. That's one. Right, what else would we have? Well, we would have just one by itself,
Just two.
just two by itself, just three by itself. You see, it would go all like that, right? Forever. But then we also have like doubles, like 1 and 2. Any subset, 1 and 3. And so on and so on and so on. And it just keeps going. You would have tons of these, right? You'd have maybe all of the evens. You'd have all of the odds. You'd have all the multiples of 3, you know, and just
So
so you can see that this looks very big compared with just the natural numbers. Okay, now a super set of the natural numbers may be countable, it may be uncountable. So we need to be a little bit open to that possibility here that this could be uncountable, even though we're on the surface of it looking at natural numbers the whole time. Does anybody have any thoughts on this? This is a little bit of a tricky one. This is a little bit of a tricky one. I'm gonna move this over here so I have only one to write. Evens here. Odds here. And this just keeps going and it's a little bit unwieldy. You have an idea?
All the subsets of n would be countable, right?
The actual sets themselves, like this is countable, right? Because it has 2 things in it. This is countable. This is, they're all countable at each set itself is countable, but that's not what we're looking at here. We're looking at the set of all of the subsets. It's a little tricky.
So it's an uncountable union of countable sets, right? And stuff.
Right, just like I could say that the real numbers, I could say that the real numbers is, you know, a whole bunch of countable sets
Right.
put together, right? But it's not a countable union of countable sets, so that's why the real numbers are not countable. Yeah. So I'd probably have to give a little hint on this one, but I'm going to see if this maybe gives you an idea. I'm gonna take this empty set and I'm gonna associate it with a big long string. Okay, so I'm gonna do that. And then I'm gonna take this one and I'm gonna associate it with a string, which is this one. Okay. And I'm gonna take this one and do the same thing. And these are strings of 0s and 1s, and the idea is I'm putting a 1 in the positions where the elements from the subset actually are. It's like this one here would be 1, 1, 0, 0, 0, 0. So this would tell me, it's like a little coding system. If I hand you this string of 0s and 1s, you're like, oh, that corresponds to 1 and 2. Or if I hand you this string of 0s and 1s, right? Then in our little secret coding system, you would know that, oh, he's talking about 1 and 3. Okay. This one is gonna be, so the even ones, So that would not be 1, it would be 2, it wouldn't be 3, it would be 4. So the evens would look like this. And the odds would look like 1, 0, 1, 0, and so on. And what I'm doing is I'm taking each of my subsets and I'm associating it basically with a bijection to a string of zeros and ones. Now, strings of zeros and ones, have we had that problem before?
Yes.
I think it was a homework problem.
Yes.
And it was done using that Cantor's diagonalization argument, right? So and by the way, when we use that Cantor's diagonalization argument, was that for countable or for uncountable? It's uncountable. It's actually how we proved that the interval 0 to 1 is uncountable. We did this Cantor's diagonalization argument. Here, it's basically the same argument, except instead of all possible digits from 0 through 9, which is the one we did in class, here the only digits that we have is 0 and 1. So for the solution, this is uncountable. And the way I would probably write it up is I would say, first of all, I would note that, let me call it capital T, which is the set of infinite sequences or strings, whichever word you want to use, of zeros and ones. So if we make infinite sequences of zeros and ones, that this is uncountable. I think wasn't that from that was like one of those extra homework problems I had to do, right? So we'll just say by homework. Forget which assignment it is right now, so do say by homework. And then what we can do is we can say there is a bijection. I'll call it F, that goes from the power set of the natural numbers to T. So we can create this bijection. Let me just say C below for a minute. The hard part of this is to explain the bijection, but then if you believe me that there is a bijection, then you can say therefore by a proposition from class, the power set of n is uncountable. Isn't that interesting? So even though n itself is countable, the power set of n is uncountable. And this bijection, so I'll just put a little asterisk here, and I have to just come down here and kind of explain it. You have the idea here, right? The idea is that given some subset S of the natural numbers, f of S, so how do I output something from that subset of the natural numbers, is the sequence with ones in the positions of elements present in S. So what I mean by that is you're gonna make a sequence of zeros and ones, right? The outputs have to be in T. So the outputs consist of sequences of zeros and ones, and where do we put the ones? We put the ones in the positions of the elements that actually are part of S. So if 1 and 2 is part of S, that's the first and second positions that we would put a 1, and then everywhere else we put a 0. If you didn't actually write this down and you just showed me a couple of examples, I would be so thrilled with that because it shows you basically know the idea behind it. I would accept that. So I would accept this kind of a work being submitted because this is a little hard to like get the right wording on it. And not only that, technically we have to now prove that it is a bijection. So we have to prove that if you give me any infinite sequence of zeros and ones, that there will be a preimage, has to be onto, and that two different subsets of n would give me two different sequences of zeros and ones. That's kind of the one-to-one part. So I won't write all of that out here, because it's kind of a pretty long-winded thing to do. But that's more or less what would be required to really fully rigorously justify it. Yeah. Does this make sense? Okay, it's kind of a nice one. Something a little different than anything we've seen before. So I thought maybe that'd be kind of fun to think about. Okay, great. So that's a little bit of practice with countable, uncountable. Make sure you go back and review these propositions. You know, if one set is uncountable and there's a bijection to another set, then it's uncountable. A subset of a countable set is countable. But not the other way around. So if the subset is countable, then the bigger set could be uncountable. Right, so just make sure you have all those things straight, because if you get them backwards, then you really are saying something that isn't gonna make sense. So, okay, super. Let's do something different. Let's take a different problem here, if that's all right with everybody. I've still got my eyes on the chat out there, guys, so let me know if you have anything you want to ask me as we go along. But let's do this one. This is number 3. Let me get this erased. Okay, so let's do this one. I'm going to make a set S here. So let S be the set of n plus 2, all divided by 3n minus 1, such that n is a natural number. And I would like to compute with proof. There's been some homework problems where I've just let people write down the answers without proof, but here I actually want to do a proof of what is the supremum of S and the infimum of S. Let's do a little bit with this for a minute. Let's compute with proof the supremum and infimum of this set S. Okay. Great. And I guess what I'll start off with is, does anybody have a suggestion with maybe what we should do first?
Plug in some numbers.
Plug in some numbers. Oh my goodness, I love that idea. And that would be, even just doing that would be worth some partial credit, right? So if you really, I don't know how to do this supremum infimum thing, you know, at least try to get something down by just writing out some elements, right? So when n is 1, I can start off. When n is 1, what do I have? I have 3 over 2. All right, so that's the first one. And then let's get the next one. When n is 2, it's going to be what? 4 over 5. And then when n is 3, we're going to have 5 over 8. And when n is 4, we're going to have 6 over 11. I'll do one more. When n is 5, I will have 7 over 14. Okay, and this goes on forever. Okay, and just make a list like so of these first few elements of the set. And you know, it might even not be a terrible idea to kind of draw these points out on a number line, so you can kind of see where everything is. There's 0, let's say, and then maybe here's 1 and here's 2, just to get my real or my integers written down. So 3 halves would be here, right? So that's 3 halves. Maybe I'll call that x1. So I know it's the first value. And then 4/5 would be right here. That's the second value. And then 5/8 is a little bit smaller than that. Maybe it's right there. It's about roughly 2/3. So I'll put that as x3. x4 is getting really close to 1/2. That's a little bit bigger than 1/2. And then x5 is 1/2. Well, you can kind of see what's going on. You can kind of see what's going on. So it looks like the terms are all kind of moving to the left. Based on that, does anybody feel confident about either of these values so far?
The supremum's gonna be 3 halves.
Yeah, so remember the upper bounds have to be greater than or equal to everything in the sequence. Well, this is kind of the rightmost value, and as we keep plugging in larger and larger values of n, right, we're only going to the left. So this x1 should be my supremum. So let's just talk about that for a second. The claim is that the supremum of S is equal to 3/2. Okay? So can we try to prove that using the definition of the supremum? I think I would like to try it. Okay, so remember that when you're claiming the supremum is equal to something, you're basically saying that it is an upper bound for the set and that it is the least upper bound, meaning if there was another gamma as an upper bound, that other gamma would be more than this one. Okay, so I want to try and do that in two parts. So let's do 3/2 is an upper bound of S. I'm gonna maybe start by trying to justify that part of it first. And then we'll worry about the least upper bound part. So i.e., let's just write out what we're actually saying. What we're saying is that we want n plus 2 divided by 3n minus 1 to always be less than or equal to 3/2. This is for all natural numbers n. That's what we're hoping is the case. Yeah. How would we be able to like prove it? This is really what we need to prove. Can we do anything to prove that one?
You could try isolating n.
Yeah, so we could like try and do some algebra with this, yeah? Of course, if we do that, if we start with this and we do algebra to it, we have to recognize we're working backwards. Because this is technically where we want to be at the end of this whole discussion. So it's okay to work backwards. We could think of it as maybe even some scratch. We could come over here and, did I spell that right? Scratch, no, I did not. Scratch. There we go. Right, so we could try and just take Brian's idea here and just imagine trying to work backwards a little bit. N plus 2 over 3n minus 1 less than or equal to 3/2. This would be if and only if. So we can actually just clear the denominators out, right? If I multiply through by 2, and then if I also multiply through by 3n minus 1, then we would just get this, yeah? Okay, and then I could, and these are totally reversible steps. So this is 2n plus 4 less than or equal to 9n minus 3. Okay, and I just go if and only if one more time. The 2n and the 9n can be reduced to a 7n on the right side. And I can add the 3 with the 4 and get 7 on the other side. And look at that, guys. We end up with 1 less than or equal to n. All of this is my scratch for this proof. Okay, so I'm proving that 3/2 is an upper bound, and I'm gonna do that basically with this scratch work. Okay, so now how am I going to do my actual write-up here? I'm simply going to say let n be a natural number. And we know that because it's given as a natural number in our set. So we know that n is a natural number. This, of course, just means that n is greater than or equal to 1. And now we just follow our scratch work. Everything here was a completely reversible step. So I'll just say retracing the scratch. Please don't spend time on the exam like rewriting it all out again, because that you don't want to use twice as much time as you need to. So retracing the scratch, we get that n plus 2 over 3n minus 1 is less than or equal to 3/2. And now we put a check on that. Okay. Just make sure you put these double arrows forward and backwards for me. If you just write them as individual statements, which is usually what my freshman students do, then I don't know how they're connected to each other, and I don't know, is everything totally reversible? So these if and only if double arrows are really important, and I think we've even seen a couple of times now when we're talking about convergence of sequences, we've seen some cases where the arrows only worked backwards. Which was still good enough for our purposes, but it would have been incorrect to just leave off those arrows. Like it might be that they only work in one direction. So anyway, am I done with the proof? Definitely not. If I'm claiming the supremum is 3/2, I now have to show that any other upper bound for S would be more than 3/2. So the second part of it is 3/2 is the least upper bound of S. And guys, do try to be a little careful with the wording. And I know this is such in a lot of your classes, you don't have to worry about this so much, but in this class, you really do. Like this 3/2 is an upper bound. I was grading some of the homeworks where people were doing these two steps, and the step one would have been 3/2 is the upper bound of S. I'm like, actually, that suggests that there's only one, but in fact, there can be many upper bounds. So that's why I'm saying an upper bound of S. But now down here, there can be only one least upper bound for S. So we can call it the least upper bound of S. Okay, so the way we do this, you've seen me do this a few times. Let gamma be an upper bound of S. Right? So we just take a random upper bound. I usually like to call it gamma. And well, we would like to show, let's just add this here. We need to show that 3/2 is less than or equal to gamma. In other words, this other upper bound that we've pulled out better not be smaller than the one that we have pegged as our least upper bound. Okay, what we do know though is that, so we know that if gamma is an upper bound of S, it just means that if we take n plus 2 over 3n minus 1, it'll be less than or equal to gamma for all natural numbers n. Right. So we know that. So I got what we know right here. I got what we want to show right here. Can we tell me how we're going to get it? We could try to follow the scratch again, but that's way more than we need to do. We have a massive number of things that we know right here. We know that this is true when n equals 1. We know that it's true when n equals 2. We know that it's true when n equals 3. What do we get when we put in n equals 1, n equals 2, n equals 3? This is for all n. We know this. I literally just put in 1 for n. What's this fraction equal to? 3/2. All right, well, it's supposed to be true for n equals 1, right? It's supposed to be true for all n's. So it's true for n equals 1. So there you go, we're done. That's the end of it. The end of it. Okay. So we don't actually have to work all that hard here in this case. Yeah, I thought about it like, well, we could take this and we could try to like isolate the n would be what it would be, and it would be in terms of gamma. And that would somehow probably be an equivalent amount of work to what we have here. And might be worth trying, but it's definitely more work than we need to do. Yeah, okay, great. So that's the supremum. Is everybody okay with this? Make some sense? Any thoughts about what the infimum of S would be? One more time? 1/3. Okay, infimum of S is 1/3. Where are you getting 1/3 from, do you think? Yeah, I kind of look at this fraction, you know, think about all the values of it. We listed a few terms here. You kind of see where are these numbers headed? They're all going downhill, right? And how far downhill are they going to get to? Well, by the time n gets huge, right? Let's say n is like up towards 1 billion or something. When you add 2 in the numerator, right, that's basically 1 billion. And when you subtract 1 from 3 billion, that's basically 3 billion. A billion divided by 3 billion is 1/3. Now, guys, all of that is the intuition. It's not going to be you're not going to make your Math 350 professor very happy with that as a total reason. But to come up with the claim, that would be a very good way to get it. Okay. It's just we still have to prove the claim. But I'm certainly happy with using your number sense and your intuition to come up with the answer in the first place. So that is the claim, and I'm gonna erase this part here so I can try and do the same thing. I'd like to kind of give you the a little proof of this as well, okay? So we're going to do, the first part is going to be 1/3 is a lower bound of S. By the way, again, even before I asked this problem on the test, I might have part A is define the infimum of S and define the supremum of S. You're going to be able to rack up some points on this exam just from the definitions and theorems, right? I mean, it's not going to be, you're not going to be able to like get an A+ by just doing that alone, but you at least will get some points going for yourself. So make sure you know these definitions of things like supremums, infimums, and so on. So let's see. We would like to show that 1/3 is a lower bound of S, i.e., I'll go ahead and just rephrase that in math notation again. 1/3 is less than or equal to everything in S. So this is n+2 divided by 3n minus 1 for all n in n. Okay. Suggestions what I might want to do with that?
Something.
Okay, just like the last one, right? Just like what we did for the supremum. I'm gonna do my little scratch thing over here again and kind of work backwards from what I'm trying to prove. So I'll probably go ahead and multiply through by the denominators to clear those out. Let me just go ahead and just say that this is if and only if 3n minus 1 is less than or equal to 3 times the quantity n plus 2. And I'm just hoping this will be true. 3n minus 1 is less or equal to 3n plus 6. Is that true? I sure hope so. Okay, we add 6 to a number, it's going to make it bigger than if you subtracted 1 from it. So over here, let's let n be a natural number. Then clearly, I was getting nervous to say that, but isn't it pretty clear that 3n minus 1 is less than or equal to 3n plus 6? So you have to put yourself onto your scratch somehow and then start working backwards. So retracing the scratch, retrace scratch to get, right? So then we're going to get 1/3 less than or equal to, and it's going to be n plus 2 all over 3n minus 1. Beautiful. Okay. So that's for any natural number, and so you've got your lower bound of S. Okay? Now, if somebody had never seen your scratch work and they just looked at this alone, they might wonder, where did they come up with 3n minus 1 and 3n plus 6? I mean, I don't see that directly here. So, but technically that's okay. Like technically that's okay because this is a true statement, and from here you just do basic algebra to get to here, which is really just this scratch work in reverse, right? But there's nothing wrong with having this on your paper. In fact, you probably should have it on your paper so that I can reconstruct where you kind of came up with your answer from. So, but it doesn't, the scratch is always off on the side. It's not like buried into the middle of the proof, because otherwise it looks like you're doing your proof like some kind of converse in reverse, right? You don't want your proof to look like that. Okay, finally, 1/3 is the greatest lower bound of S. Let's give this one a try. And so here's where we do the gamma thing, right? So let gamma be a lower bound of S. And we need to show WNTS, you're certainly allowed to to use that, we would like to show that gamma would be less than or equal to 1/3. In other words, 1/3 is the greatest of all of the lower bounds. Yeah. Okay. And what we know is that gamma is less than or equal to everything in S, right? So we know, let's just add that to our write-up here. We know that gamma is less than or equal to n plus 2 divided by 3n minus 1. And guys, I can give you partial credit for every single thing you're doing here, right? So even if you don't see the whole solution right in your head at the beginning, don't let that throw you off, or don't get discouraged or say, oh, I'm just going to skip this problem completely, right? The only way I can't give you any points is if there's nothing there, right? So just get it a start, give it a start. So we're going to grab this lower bound of S, we're calling it gamma, we write down what we need to show, that's good, I can give you credit for knowing that. We write down what we already know, that's also good. And by the way, this is for all natural numbers n. So all of that is really, really helpful. Okay, so what do we know here? Last time on the Supremum one, all I did was plug in n equals 1 and I was done. Am I going to be done this time if I do that? If I plug in n equals 1, what I will say is that gamma is less than or equal to 3/2, and that will be correct, but unfortunately it's not what I want to show, right? I actually want to show that gamma is less than or equal to 1/3.
Limit?
Pardon?
Do you use the limit?
Yeah, this one's a little trickier. This one's a little trickier. Like you might say, well, what would happen if I plugged in n equals 1,000? So then we would know that gamma is less than or equal to 1,002 divided by 2,999, right? Just as an example. And that would be true. However, this is still too big, right? It's still bigger than 1/3. So 3/2 is obviously not a strong enough upper bound over here, but even this isn't good enough. There is no single value of n that you can plug in. I can say, well, what if I plugged in 1,000,000? Then I'll get a fraction here that's closer to 1/3, but it's still going to be a little bit, just a hair more than 1/3. And I'm going to have that skeptic in me saying, well, what if gamma is more than 1/3, but somehow less than this? Right? I have not convinced myself yet that that couldn't actually happen. So yeah, we kind of have to take a limit in a sense, but we need to make it a little bit more rigorous than that. So what I'm actually going to suggest here is that we proceed by way of contradiction. Okay, because you can plug in n values forever, and any individual n value will never allow you to draw this conclusion. And so we need to be a little bit more careful. So the way I'm going to do this, assume by way of contradiction that gamma is greater than 1/3. What I would like to do now is find an n that is big enough to contradict that, right? So if gamma was, say, 0.333335, right? That'd be bigger than 1/3. Then I'm pretty sure I could find an n eventually such that this fraction would actually be less than 0.333335. And so you'd have a contradiction to gamma being a lower bound of S. So I'm going to maybe need to do a little bit of scratch here. So let's take what we know here for a minute, and I'm going to do basically what one of you suggested a few minutes ago, which is I'm just going to try to solve this for n. Because it'll tell me kind of how to choose an n based on gamma, right? So I'm gonna go ahead and cross multiply this one. So 3n minus 1 times gamma less than or equal to n plus 2. Okay, and then this is if and only if. Let's get this n factored out on the left side. There's a 3 gamma minus 1 that we would have on the left side, and then on the right side, I'll have a 2 still, and I'm gonna add gamma to the right side. Okay, and then from there, n would need to be less than or equal to 2 plus gamma divided by 3 gamma minus 1. I think I did that correctly. Does that look okay? And what we know is that gamma is bigger than 1/3. And this is for all natural numbers n, all the way down, okay? So seems a little bit weird, doesn't it? Let me see. This is for all natural numbers n.
If you figure gamma too much bigger than 1/3, then it's too small and it's not a natural number.
That's what I'm wondering. Yeah, I think that's really, really true. Like we could actually imagine some choices of what gamma could be. What if gamma was equal to 1? This is still scratch. This is still scratch. I don't know that gamma is equal to 1, but let's just say it is. If gamma was equal to 1, what would we have here? We would have n is less than or equal to 3/2. Okay, that's not going to be true for all n. Right, so this has to be for all natural numbers n. Right? So that wouldn't be true. What about if gamma was 1/2? Then we would have n is less than or equal to, well, 2 plus 1/2 is 2.5 divided by 0.5, I believe, which would, this would give me 5 now. Now, that's also not true for all n. Now, if gamma was, let's pick something that's actually less than 1/3 and just see how that would play out. Let's pick 3/10 for a second. By the way, we cannot choose gamma equal to 1/3 because you'll end up dividing by 0. Okay, but imagine for a minute that gamma was 3/10. Then what you would have is n is less than or equal to 2.3 divided by, put 3/10 down there. I'm gonna have 9/10 minus 1. That's negative 1/10. And so what is this actually going to be? N is less than or equal to negative 23, right?
Yeah.
So if I just multiply through by 10, you'd have 23 on top, you'd have a negative 1 on the bottom, that'd be negative 23. Well, that's not true either. Yeah, I mean, that's definitely not true for all n's. Except that there's a little problem with that, which is that if gamma was equal to 3/10, what did we do from here to here? We divided by 3 gamma minus 1. Now, as long as 3 gamma minus 1 is positive, and you divide both sides by a positive number, your inequality stays the same direction. But if you divide by something that's actually negative, in this case, if gamma was 3/10, this is negative 0.1, this would need to have been flipped over. You see, so n would be greater than or equal to negative 23, and that is true for all n. So for a gamma value that is less than 1/3, everything's cool. Right? But if gamma is greater than 1/3, then this inequality stays in this direction, right? This is a fixed number, right? That not every natural number will, I mean, we actually have the Archimedean principle that says if you give me any number here, I can find an n that would be greater than that number. And that n would be a contradiction to this structure. Right? So let me just erase all of this. Do you see what I'm saying? This is a little tricky. Probably if I was gonna do this on the test, I would just say, tell me what these things are, and that'll be fine. I just wanted to practice the definition. Anyway, so what we can say here is that actually, let's actually come back to the main proof here. Let's just come back to the main proof. Right here, okay? By the AP, there exists an n naught in the natural number, some fixed natural number, with n naught greater than or equal to 2 plus gamma divided by 3 gamma minus 1. And so that is a safe number to write down because we are assuming by way of contradiction that gamma is greater than 1/3. Okay, so this is a legitimate number, and there'll be an n naught that's greater than that. Okay, and so then from there, so thus, I'm gonna multiply through now by 3 gamma minus 1. 3 gamma minus 1 times n naught is greater than or equal to 2 plus gamma. And then I'm going to rearrange this equation as thus 3n minus 1 times gamma, n naught, sorry. 3n naught minus 1 times gamma is greater than or equal to n plus 2. I'm basically retracing the scratch work, but it's with the inequalities the other way around, right? And so this means that thus gamma is greater than or equal to n plus 2, n naught, so these should be n naughts. All of them are n naughts. N naught plus 2 over 3 n naught minus 1. That's not for all n naughts, that's just for this one n naught that the AP gave me. But this is a contradiction to the assumption here that we know that gamma is supposed to be less than or equal to all of those. So this is a contradiction. Oh, took a little work. Okay. Does that seem reasonable?
I have a question with,
Yeah.
how did we get from the 3n minus 1 times gamma to that next line?
This is just algebra. If
Did
you
we
multiply out the left side and then gather up all of the n terms, you'll have this many n's on the left side. So because this is 3n gamma, and then there's one n here. So if you subtract it over to the left side and then factor the n out,
We did everything. Okay, perfect.
I just kind of did that all in once.
Okay, got it, got it.
Exactly. So how does the proof go? Assume by way of contradiction that gamma is greater than 1/3, right? And then use the Archimedean principle to find an n naught such that n naught is greater than this number. Where in the world did anybody dream up this number? Well, that was from the scratch work. Okay, so you've got this n naught that's greater than or equal to that number, and then you just work with that algebraically until you find out that, oh, well, that would mean that gamma is greater than or equal to this guy, and I see one slight little goof in my proof. Does everybody know what it is? I need to fix one little thing I just realized. When I say gamma is greater than or equal to this, it could be equal to it. And if it was equal to it, I wouldn't be contradicting the assumption that gamma is less than or equal to all of those. So I'm gonna make my AP principle a little bit better and just say that the n is strictly greater, and so these should all have been strict inequalities, guys. I am sorry, that is just a little typo on my part. Very minor little thing. Okay,
So if we say we know that gamma is less than or equal to n plus 2 over 3, and then we
That-
go by way of contradiction, we're only contradicting that it's less than or equal to 1/3.
right, we're contradicting the thing we're trying to prove.
Okay,
So we're trying to prove that gamma is less than or equal to 1/3. So that by way of contradiction would say, assume gamma is greater than 1/3. And then from there, we pull out this Archimedean principle to find this natural number that's greater than this thing, which nobody would dream up in their head. That's coming from the scratch work. And then from there, you just rearrange the scratch work until you have the contradiction. Yeah, so it's not so crazy after all, but that is how that works. Are there any questions out there, guys?
Where do you want the BYOC stabbed in? After.
So where does this go? Okay, so how is this supposed to be written up? We need to show that gamma is less than or equal to 1/3. I would stick this right at the end of that sentence. Yeah. So as soon as you state what you're trying to prove, then you just say, by way of contradiction, suppose that gamma is greater than 1/3. Okay. This one might take a little hint, to even know to do it by way of contradiction is maybe not like totally obvious. So anyway, okay, let's do another problem. Or am I okay to move on? Okay, I'm just gonna keep cranking through. I love these problems. I'm just glad somebody's here to listen to. Let's do, I'm trying to cover everything that we've talked about, at least in some way, shape, or form, before I cycle back to do any repeating of anything. So I think I'm up to number 4 now. And what I want to do here is, I'm going to make a sequence this time. I'm going to let xn be equal to 3n squared plus 7n plus 5, all divided by 8n squared plus 3n. And I would like to find and prove the limit of the sequence. Or show why it diverges. Diverges is, I don't know that I ever actually used that word in class. It just means doesn't converge. So now we're into the chapter 3 stuff, and we want to either prove that it doesn't converge, or if it does converge, we want to find the limit and then prove what the value of the limit is. So the first thing is going to be to make a decision about whether it converges or not.
Are you gonna specify like what method you want us to use?
So far I have. If I don't specify it, you get to do it however you want. It's kind of, it's good and bad. It's, if I tell you what method to use, then you sort of like have a safety net. Okay, I know this is what I'm supposed to be doing. But then if it's something you don't want to be doing and you'd rather do it a different way, then you're kind of out of luck there. So I don't usually like to create questions where I say, oh, do it this way. Because, in math, we're supposed to be able to prove it whatever way we can. So yeah, for now, let's just do it however we want to do it. Let me take a straw poll here. How many people think that this does converge? Okay, what do you guys in the, okay, Ayushi's got a hand up. Danny's got a hand up. Okay, good. So I got a few people with hands, at least a majority with hands up. So those of you who think it converges, then you have to tell me what you claim it converges to, because that's going to be what we have to prove.
3.
3/8. Okay, great. By the way, and this is correct. All of this is great. And just even writing this down, you'll get some partial credit for it. So definitely do that. Really the key thing you need to look at here are the powers of n. If the powers of n in the numerator are more than in the denominator, then it's going to diverge. right? If they're the same, if there's the same powers of n on the top and on the bottom, then you just take the ratio of the leading coefficients. And if the denominator is actually the higher power than the numerator, then what's the limit going to equal?
Yeah.
Just zero, exactly. So this is stuff you probably saw in calculus, just kind of some intuition based on that. Okay, so this is the claim, and I would like to know, how would you guys like to prove it?
Divided by n squared, technically.
Okay, so we'll start off, xn can be basically rewritten as 3 plus 7 over n plus 5 over n squared, all over 8 plus 3 over n. So we can certainly do that. And now what?
You can use the limit law to say the limit at the top times the limit of the denominator.
Okay, by the limit theorems, remember that the limit theorems tell us that limits respect addition, they respect scalars, they respect division, all of the things that we see here. By the limit theorems, the limit of xn as n goes to infinity, this is just another way of saying, you know, what the convergent value is, would be equal to the limit as n goes to infinity of the top part, which is a 3, plus the limit, actually, let's pull out the 7 as well. 7 times the limit as n goes to infinity of 1 over n, plus 5 times the limit as n goes to infinity of 1 over n quantity squared. Remember, limits respect power multiplication, so 1 over n squared is the same as 1 over n times 1 over n, and then this is all over the limit as n goes to infinity of 8 plus 3 times the limit as n goes to infinity of 1 over n. So. All right, and then, so that's by the limit theorems, and then this is just going to be very easy because the limit of 3 is just 3. You guys are allowed to use the fact that the 1 over n converges to 0. So this is just 7 times 0, and then plus 5 times 0 squared. And then on the bottom, we have an 8 plus 3 times 0. So you can just use that information. And yeah, that's just going to be 3 over 8. That's just going to be 3 over 8. So that's a good way to do the problem. Okay, yeah.
So it's doing like the math, like a good proof, or do you want like that, what is it, the epsilon?
Well, this goes back to his question. Brian was asking me, do you have to do it a certain way, or will I let you do this? It sounds like you guys want to do it the hard way. Okay, let's do it the hard way. We're gonna do it again. At least two people in the room. You can blame these guys. They don't like this proof because it's just not using the definition. So we'll use the definition to do it. No, you're good. You're good. I wanted to do this. Just trying to blame me for it. I wanted to show you the other way to do it more directly as well. So this is good practice, okay? But is everybody good with this method? Okay, everybody's good with that. Just be a little careful. Okay, I would like to show you, okay, just a look before I do the second solution. I have a quick little warning for you. What if I say find the limit as n goes to infinity of n minus n? Now, that looks a little silly. You're probably looking at this and, well, that's just 0, right? But if I used the limit theorems, if I tried to use the limit theorems, what would be wrong with this? I've never done this on an exam. Maybe I should try it sometime. Write up an actually a wrong proof and have you guys tell me what's wrong with it. But why can't I just do my limit theorem here and just say that I can just do these limits separately, and this of course is dne. Basically it's infinity, it doesn't have a value. And you know, if nothing else, you would just say it's that. And we all know that infinity minus infinity is indeterminate form. It's not necessarily equal to 0. So what would be wrong with doing this. Yes,
N and N are two separate sequences and both of them don't converge, so
correct.
you can't use limits.
You can't use the limit theorems unless all of the sequences that you are either adding, multiplying, dividing, subtracting, or scalar multiplying, or whatever, they all have to converge first, right? So there's a homework problem on, I think it's for tomorrow night, where I have like xn and yn. And the assumption is that xn plus yn converges and also xn minus yn converges. And then you're trying to prove that both xn and yn converge separately. But you have to, you can only use the limit theorems on the things that you know converge to begin with. That's an important point. So this would not be good, right? Basically, the limit theorems cannot apply. You cannot apply these limit theorems unless all individual sequences converge to begin with, right? All individual sequences converge first. So the limit theorems are great, but you just have to make sure. So you come back over here, you know, does this limit exist? Does this limit exist? Does this limit exist? Every single one of these, and they all have to exist first, and then you're allowed to use that theorem and break it apart. Okay, but yeah, let's, I'm gonna erase this proof and let's try and prove it just from the definition. Maybe I will ask you to just prove one from the definition, okay? So let's go back and let's do, I'll call this proof number 2. I'm just gonna do a second proof of this same thing, just to practice a little bit. So you remember the definition way, what's the rubber stamp opening sentence?
Epsilon greater than 0.
Yeah, let epsilon greater than 0 be given. Okay, so we start with that. And then our job is to find this, what is it, at the n naught, right? So I'm gonna come over and do my scratch. You remember we always have to sort of go over to the side for a minute and do some scratch work on this one. Okay, so for the scratch, what is it? I need absolute of my xn, so that would be 3n squared plus 7n plus 5 all over 8n squared plus 3n less, oh, sorry, minus, I have to, remember you have to subtract the limit value, which is 3 over 8, and all of that less than epsilon. Okay, let's just practice how this would play out. This one's gonna be a little interesting. This will be a little bit interesting, not totally straightforward. What would you probably do first here? Yeah, get my common denominator. Okay, so my common denominator, I have an 8 multiplied by 8n squared plus 3n. And then in the numerator, I have to like cross multiply a little bit, right? So 8 times the quantity, 3n squared plus 7n plus 5, minus 3 times the quantity, 8n squared plus 3n. All of that less than epsilon. Can you guys all read this okay? Zoom world out there, I hope. I'm a little tight on space. I should never have started right there, but that's okay. Actually, I might end up continuing over here, so I don't have to mess with any of that other stuff. Yeah, I'll be able to do that. Okay. Let's clean this up a little bit, and I hope that it will be made a little bit nicer anyway. I'm gonna leave the denominator alone for a minute. Hey. Oh, actually, let me do one thing. Would you guys all agree that the denominator is always positive? There's an 8 and then there's just plus signs with n in it. We don't really need to put the absolute value bars around that denominator. Let's just go ahead and write it as 8 times the quantity 8n squared plus 3n. Nothing wrong with doing that. And then in the numerator, well, I've got 24n squared and 24n squared that are going to cancel, right? And then so what else do we have here? I have a 8 times 7 is 56, but I'm also subtracting 9 times n, so 56 minus 9, it's getting too late. 47? Yeah, 47. Okay, 47n. And then what else do I have to deal with? Plus 40? So I actually don't need the absolute value bars anymore. All that stuff is positive to begin with. This is what we're gonna have. Okay. And normally the way we try to work with these, right, is we usually try to find a common, well, we try to solve this for n. Right? That'd be sort of the next step. But as you can see, I'm not too excited about just solving that for n right now. So I'm going to try to compare this with something that's simpler than it, but which is more than this. I'm gonna try to make so instead of solving for n, I'd get some ridiculous quadratic equation eventually, right? Instead of doing that, well, you could do that, by the way, you could do it. But we can make our life a lot easier if we just say, you know what, we're gonna replace this with something that would imply this. So I'm gonna do my scratch work over to here too, guys, sorry. The scratch work is the key to this proof. So I'm going to do this. I'm going to try to replace this left-hand side with something that is bigger than this one. Well, one way to make this bigger, to make this fraction bigger, I have sort of two tricks of the trade. To make this fraction bigger, I can either make the numerator bigger, or I can make the denominator smaller. Or I can do both. I'm going to make the numerator bigger. You know how I'm going to make it bigger? Instead of adding 40, I'm going to add 47n. I already have 47n. I'm going to add another. Actually, you wouldn't even need to make it 47n. You could just make it 40n. You can make it 40n. In other words, 87n. Right? If 87n was less than epsilon, then surely 47n plus 40 would be too. Because this is actually smaller than this one. And remember, I want my scratch work to work backwards, because this is where I want to end up. So I'm making something bigger here, right? And then what am I going to do? The other way I can make the overall fraction larger is if I make the denominator smaller. Well, you know what I'm going to do in the denominator? I'm just going to do the 64n squared part and just forget about the plus 3n thing. I'm just going to write it as 64n squared on the bottom. Just stop with me for a moment and just convince yourself, if this was true, would this be true? Right? If we know this, then would it work to then make my numerator a little bit smaller and also to make my denominator a little bit bigger? Right? So if this is true, then this would be true. And why I like this one, of course, as you can see, I'm going to simplify this a whole lot nicer than dealing with this quadratic thing over here. All right, so now I'm going to go, sorry, a little bit more room here. If and only if, let's see, I can cancel an n here, right? So it's going to be 87 over 64n less than epsilon. And I'm going to go over here even a little bit more. I'm sure glad I have a big board here to do this with. I want to solve that for n. So let's flip this thing over. And so 64n over 87 greater than 1 over epsilon.
I think that should be.
Oh, 64, sorry. 64n, thank you. 64n over 87 greater than 1 over epsilon, and then this would be equivalent to n greater than what, 87 over 64 epsilon. Okay, I'm gonna finish my proof right here. So by the AP by the AP, there exists an n naught in the natural numbers with n naught, what, greater than 87 over 64 epsilon. Right? And if somebody just walked in the room right now and all they saw was that, they'd be like, where did you get that from? Right? Well, it's really the guts of the actual calculation is right here in the scratch work, yeah? So now I'm just gonna say let n be greater than or equal to n naught. So thus, if n is greater than or equal to n naught, then it is also greater than 87 over 64 epsilon. And now we can retrace our scratch work. Retrace scratch to finish the proof. Wow. The tricky step really is this one right here. This one backwards step. When you're dealing with fractions and you want to make them larger, you can make the numerator bigger or you can make the denominator smaller. So in going from left to right, yeah, I've gone the other way around. I've made my numerator smaller. I've made my denominator bigger. This fraction is less than this fraction. And if this fraction is already less than epsilon, then surely something even smaller will be less than epsilon. That's the idea. It's a clever little idea. Okay. Very good. Yeah. Time is it? Oh, we still have a little bit of time. Any questions? Yeah, Chris.
Just wanna clarify,
Uh-huh.
I know we can make things smaller to make it fit in the epsilon inequality.
Yeah.
How can you guarantee that if you make something bigger, it's not bigger than epsilon? Or is that just?
So I understand what you're saying. You're like worried that, well, maybe we've gone too far here. Like we made the numerator bigger, we made the denominator smaller. Now we have this bigger thing. And maybe it's no longer going to be less than epsilon. But the idea is that eventually it might mean that the n that we need to sort of find with our Archimedean principle is going to have to be a little bit bigger than it would have, if we really wanted to find the best n to make this true, maybe it wouldn't have been the same n as the n naught that we pulled out here, right? We've lost some information, right? We've replaced this with something bigger. So yeah, maybe we have to make our n larger to get this to be true than what we really would have needed for this one to be true. Okay, that's true. You're losing a little bit there. But remember, the definition of convergence says there exists an n naught. Nobody ever said you had to find the best one, the smallest one. Just any n naught whatsoever will satisfy that definition. So that's why I could be kind of relaxed about that and allow myself a little wiggle room with that expression. That's a real good point. Yeah, good comment. Is that okay? Yeah, okay. Fantastic. Everybody out there okay? Okay, I don't see much in the chat so far. I want to do one. I did one soup and in problem already. I guarantee you there's going to be one on the exam. That homework that I'm just now grading, homework number 5, has like several good problems on it. I want to do one more to practice that. I just really want to make sure everybody can do this. And this will be perfect to kind of wrap up this session. And then we'll have, on Wednesday, I'm gonna do some more problems. I'll try and do some different problems. Again, totally optional. Maybe by Wednesday, you guys won't wanna do it, but I'll just do it anyway. Okay, so let's suppose that A is a subset, a subset of the closed interval from -10 to -1. And where is it here? B is a subset of the interval from 1 to 10. Okay. And I am going to define something called the absolute value of A times B. Okay, and so this is something we've never talked about in class. I'm just making up a definition here. So this is all I'm going to do. It's just a set of all expressions of the form absolute value of little a, little b, such that little a is in capital A and little b is in capital B. And what I would like to do here, guys, is I would like to prove that the supremum of this set, capital absolute value of capital A, capital B, is equal to the negative of the infimum of A times the supremum of B. Oh, okay, so it's kind of abstract. Now, notice, before I do anything else, notice I didn't say that A was equal to if A was equal to this interval, then of course its infimum would be -10. And if B was equal to this whole entire interval, then its supremum would be 10, and we would have -100 here, right? -10 times 10, right? And in that case, you take all of these, I'm sorry. Sorry, if these were equal, then the infimum of A would be -10, the supremum would be 10, I'm sorry, it would be positive 100. I think I said -100. It would be positive 100, and that's exactly what this would be. Because if you take the entire interval here and here, and you form all possible products, it's like, well, what's the biggest one you could get? Well, -10 times 10 would be -100, its absolute value would be 100. And so it would be easy in that case. But we don't know what A and B actually are. They are just subsets of these intervals. And so that's why this proof has been stated kind of abstractly rather than putting any numbers in anywhere, because we don't actually know what this number is. We don't know what this number is, and we don't know what this number is. It all depends on what A and B are. Okay? If you see a problem like this on the test, which you probably will, something like this. I mean, how many, we've had, you had a homework problem dealing with something like this. Right, there was the one about inf of A plus B equals. The more times that you see me do these and the more excited I get about them, right, the more likely I might want you to try one like this for yourself. Okay, so we've seen a few of these, and now I'm gonna do one more for you. And I just want to remind you kind of how to set it up, okay? The first thing is you need a little notation here. And what I would do, the way I would recommend the notation is I would say, let's let alpha equal the inf of A and beta be the sup of B, supremum of B. Okay. Technically, you don't have to introduce that notation. Like you can just live with writing these words out everywhere, but it's just, I think, nice to do this because then you don't have to write as much. And then the claim just becomes, what you're really proving then, guys, is that the sup of absolute of A times B is just negative alpha beta. That's what you want to do. Okay, so let me give myself some room. And we really want to try, I've seen a few variations in the homeworks that have been submitted. Again, I've only gotten about half of them graded so far, but I've seen a few variations on sort of the template that I like to use, and that's okay. It doesn't have to be exactly the way I write it, but I like this template and I would recommend it for sure to do this in two parts. The first part is to prove that this guy is an upper bound for the set, and then that if there was a gamma that was in an upper bound, that this guy is less than or equal to gamma. That's the way I try to do this. So in two parts, right? So the first part is negative alpha beta is an upper bound for absolute A times B. So this is what I want to prove first. This is the first part. Oops, sorry, guys. Sure, don't block all that. So to prove that, and again, part A of the question might ask you, what's the definition of an upper bound? So you're just going to have to take an arbitrary element out of our set. So this is the key thing we're working with right here. You're going to take an arbitrary thing out of this set and show that this guy is bigger than it. Okay, so let's see. Let's let absolute little a little b be an element of absolute capital A capital B for some little a in capital A and some little b in capital B. Okay, so we're going to start off that way to get this thing rolling. Okay, so ultimately going to need to use where the little a and the little b live. We've already got a lower bound for capital A. We've already got an upper bound for capital B in place. So doesn't that tell me that we know. But we know therefore that, what will it be? Alpha will be less than or equal to little a. Because alpha is a lower bound in Feynman, that means lower bound of capital A. And at the same time, beta is an upper bound for B. So beta would be greater than or equal to little b. What I'm really trying to prove is that negative alpha beta is greater than or equal to this guy. So any suggestions what maybe I need to do here?
You can multiply negative to the alpha A inequality,
So I can take this one and multiply it through by
-1.
-1. Okay, so exactly. So I could rewrite this as negative alpha greater than or equal to negative a. Right? So negative alpha is greater than or equal to negative a. And beta is greater than or equal to b still. By the way, everything is now positive. A lived in A, which was some negative number. So negative A is positive. B is positive because B comes out of capital B. So if I were to multiply these, I'm just trying to say what I really want to do now is multiply the two inequalities together. But when you do that, you got to make sure that you don't have a sign flip that happens, right? But here, everything is positive. This is a positive number greater than or equal to a positive number, and this is a positive number greater than or equal to a positive number. So you can just multiply them together. So thus, negative alpha times beta is greater than or equal to negative a times b. And because a was negative, this is actually a positive times a positive. So if I now decide to put, I'm going to multiply those two together. Of course, if I multiply them together right now, then it's actually negative again, but I got to put absolute value bars on that to make it positive. So that's actually equal to that. All right, keep in mind, little a times little b is negative. Because little a lives in capital A and little b lives in capital B. That means one of them is negative and one of them is positive. So when you multiply them, it's actually negative, but I can take the absolute value of that and it becomes positive. Yeah. This is actually a positive number, which is the same positive number you would have gotten if you had just multiplied A and B originally and then just taken the absolute value of it. Yeah, okay,
Dr.
great.
Henry,
That checks that off. Question out there?
yes, can you, I'm just confused how negative a is considered a positive number.
Well, little a itself lives over here, right? Between -10 and -1.
Mhm.
So if you take the negative of that, it's actually going to become a number between 1 and 10.
Okay, I see it now.
Right,
Thank you.
so right, negative a is actually positive, b is actually positive, this is actually a positive number. And I would obtain that number also by just taking a times b and then hitting it with absolute value bar.
Okay, perfect. Thank you.
Good question, you bet. Okay, so this is the first part. So now let's go to the second part, okay? And then this will pretty much bring us to 9 o'clock. So let's suppose we have another upper bound. So for part 2, well, sorry, before I go to that, let's just write down what it is we're going to prove. Negative alpha beta is the least upper bound of absolute AB. This is the second part of what we have to show. Guys, if you even just write down the outline with the two parts and you don't even do the parts, if you show me that you know what you need to do, I can give you partial credit for that. I'm just trying to really encourage you to just show as much work as you can. Try to write as much down. Okay, so to do this part, let's let gamma be an upper bound for absolute AB. And so, of course, we need to show that negative alpha beta is actually the least of those upper bounds, less than or equal to gamma. It's what we really ultimately want to show here. Okay, well, gamma is an upper bound for this set. So that means, let's write down what this means. So we know that gamma is greater than or equal to everything in this set. That would be absolute little a little b for all little a in capital A and little b in capital B. Okay, so we would know that much already. Okay, and by the way, we can get rid of those absolute value bars right away because we already know that B doesn't need the absolute value bars, and we already know that A actually does need the absolute value bars. What would happen is it would become negative A without the bars because A was a negative number. So we can literally just make that replacement. This is for all A and for all B and B. Okay. What we have so far. Okay. And this is a positive times a positive. Anybody think they have a way of making an upper bound for capital E out of all this? Can I just tinker with this a little bit? What do you want me to do?
Alpha over A.
Let's divide by net. If I divide by a positive number, I don't have to change the sign. So let's just divide by negative A, right? So then this is just gamma over negative A greater than or equal to B. This is still for all A and B and B. You've seen a problem very similar to this in homework already. Oh, well, look at that. I have something that is an upper bound for B. But the least upper bound for B is beta. So what I know then is that this upper bound for capital B, so let's just write it down. So gamma over negative A is an upper bound for capital B. And thus, beta is less than or equal to, and by the way, you can put the negative out in front. You don't have to put it with the A all the time. So it's beta is less than or equal to the negative of gamma over A. This is for all fixed A. So for every little a, we would know that. All right. Well, we're getting there. But let's get rid of this fraction. I'm actually going to multiply the a over to the other side here. Actually, let's just multiply negative a so I don't have to do a sign change, right? So I'm just going to multiply through by negative a. So then negative a times beta is less than or equal to gamma. This is for all little a and capital A. Now, what maybe should I do? I've already used the least upper bound for capital B, but what I have not used yet is a greatest lower bound. I have not used the fact that alpha is the greatest lower bound of A, right? There's no alpha here yet. Okay. So what I probably want to do is find a lower bound of capital A and then compare it with alpha, which is the greatest of the lower bounds. So do we have a way of getting a lower bound for capital A by tinkering with that inequality? Divide by negative beta. I like that idea. So let's do that. Divide by negative beta, and I'm gonna make a mistake on purpose and see if anybody catches me. Then divide by negative beta, I have something like this for all A and A. That look good? Do you know what I did wrong?
You gotta flip the equality.
Now I actually do have to flip this inequality, right? Because after all, negative beta is a negative number. If you divide an inequality by a negative, you have to flip the sign over. So this needed to be a greater than or equal to gamma over negative beta, but that's actually a good thing because that means we now have what? We have a lower bound for capital A. Whereas the greatest lower bound is alpha. Okay, so gamma over negative beta is a lower bound for capital A. And so by definition, we're running out of room here. Negative gamma over beta by definition would be less than or equal to alpha, which is my greatest lower bound for capital A. And now I just need to, this is what I'm trying to prove. I mean, anywhere getting to it. I'd multiply through by negative beta. Except negative beta is negative, right? Because beta is positive, so this actually has a sign change. Oh, perfect. That's exactly what I wanted. Sorry. Yeah, so you just multiply through by negative beta in that last step and you get exactly what you needed. This one's a little annoying because there's this negative and these inequalities, there's a sign change when you flip. Sorry, there's a flipping of the inequality when you multiply through by a negative number. If I wanted to be nice, I would just make everything subsets of the positives, and then we would have a nicer statement. If it was subsets of the positives, then it would probably just be sup of this is equal to sup of A, sup of B, and there'd be no minus sign, and it would just be sups. But I wanted to create one that had both sups and infs in it at the same time. It's like good practice to kind of put it all together. So, does this make sense to everybody out there? So just make sure you can do this kind of problem, and that homework that you turned in last week, which I'm still halfway through grading, had some really good examples on it as well to take another look at. And yeah, it is 9 o'clock, and I don't want to go too long because I do have office hours for both of my classes here. But we've done some good, I've made some really nice progress through these problems. I do have a few more, but I think I'll save those. Give you guys, this is enough to chew on. I mean, it's 9 o'clock at night, right? So maybe it's best that we take a bit of a break until we are all fresh again to try some more problems. Does anybody have any questions about any of this?
The questions are different from the review pack or the review problems in the midterm that you have on.
Absolutely, yeah, these are gonna be different problems, right, yeah. So just when I'm thinking about the test, we kind of have three parts to it, right? There's the chapter 1, which is the stuff about sets and functions. That's really kind of review material. You might see about a quarter of the exam on chapter 1. I have not written the test yet. I'll write this down. I've not written the test yet, so I can't tell you for sure. But just so you kind of, I hate for the exam to be like just so much full of surprises. So I would say chapter 1 might be approximately 25% or so of the exam. And I might give a little more. I might give a little bit more to chapter 2, maybe closer to 40%. There's quite a bit there. There's all that stuff about sups and infs, like the stuff we were just covering, but you also got all the inequalities, the stuff on cardinality of sets, which is also in chapter 2. So this is a pretty big chunk here. And that just leaves maybe about 30% for chapter 3. That does not add up to 100. I'm not doing the math. Okay.
Percent is given.
How about we, yeah, right, yeah. How about we do something like this? I don't know, I hope that adds up right. Anyway, something like that. Don't quote me on this. This is just a rough idea. I think chapter 2 is where we spent the most time. And then maybe second most time would have been on chapter 3. And then, but just don't discount chapter 1, because the thing is, the chapter 1 stuff, you got to be able to do functions and sets kind of with all the material, right? It's like prerequisite stuff. So I would not say, oh, I'm not even going to study chapter 1. That wouldn't be a good idea, right? You should practice images, pre-images, unions, intersections, and there's some nice practice in the group work. As well as in some of those first couple of homework assignments. So I would look at some of that too. But I'm really super stoked to have so many of you here, both in more than half the class, like between who's here and who's in Zoom. That's more than half of you. So I'll post up the video for the other half if they want to take a look as well. And then yeah, I think I'll leave it at that. I'm just gonna switch over to office hours, guys. Is it okay if I end this session and then I'll go over to the Zoom room for my office Zoom?
Thank you.
Thanks for coming, guys.
Thank you.